Okay, so we'll go ahead and get started on the slides here. And again, this time we're estimating standard deviation. And as I just described, it uses the chi-square distribution. That distribution is not symmetrical, so we won't be able to add and subtract some margin of error. Instead, we'll directly calculate the bounds. This just tells you how chi-square is calculated based on a random sample. Just like last time with the means, this is going to depend on the sample size n, and we'll have to use degrees of freedom, and we always use n-1 degrees of freedom whether we're calculating an estimation for a mean or a standard deviation. Okay, so just to bring up the characteristics again here, it's not symmetric. And the shape depends on the degrees of freedom. So as we increase the sample size, obviously the degrees of freedom is just one less than the sample size. So saying that it depends on degrees of freedom is the same thing as saying it depends on the sample size. And the larger the sample size, the shape becomes more and more like a normal curve, but it stays skewed right, and thus we can't use a margin of error. As the number of degrees of freedom increases, we do get nearer to the symmetry, but not quite. Okay, and here's a picture with an example. So 2 degrees of freedom, implication there is a sample size of 3, which is ridiculously small, but we get a really poor curve to try and find. I mean, there's just not enough information there to try and find an estimate for the standard deviation. As we increase our sample size or degrees of freedom, let's move on up to 10 and 15. So with 10, it's skewed right. And with 15, this green one, it is still skewed right, less so. And then with the purple, the skewed right is less pronounced by a long shot. Okay, so we use what we call the critical values. Critical values are what we use in the calculation of the bounds for our confidence interval. So we have to learn how to find critical values before we can develop our confidence interval. So we want to find the chi-square values that separate the middle 95% of the distribution. So if our shape is something like this, a little bit skewed right, then maybe this has got 0.025 area. That would be the 2.5% on the left. And then on the right, since the tail is not as, theoretically not as far, maybe it's here. So this area is the other 0.025. Okay, so that represents 2.5% in each tail, the right tail and the left. Okay, so notice that's not necessarily the same distance away from some perceived center. So margin of error looks different here to here. So what we do is we go find it in that table, and the chi-square that we need is 0.975 to the right. So if I translated it so that it was the area to the right, I would actually be interested in 0.975. Now on this side, I can go directly with my alpha 0.025, or my alpha over 2 in this case. Okay, so basically what this is chi-square of alpha over 2. And this is chi-square of 1 minus alpha over 2. So since we wanted 95%, alpha equals 0.05. So this is 0.025 because that's what alpha over 2 is. And this is 1 minus 0.025. And the reason we need that is because our table that we're going to consult gives us the area to the right of the subscript of chi-square. So let's go look that up. They've given us the results, but let's go look it up in the table. I went ahead and copied the table down here on the last slide, so I'm going to go there. Okay, so here's our chi-square. And the thing that we're missing is the degrees of freedom, so let's go back here. And it's said to assume 18 degrees of freedom. So why do we assume 8 degrees of freedom? Who cares? They just told us to use it, so we're going to follow their instructions. So with 18 degrees of freedom, if I do chi-square of 0.025, yellow please. Okay, so there's 0.025 and chi-square at 18 degrees of freedom is 31.526. And then 1 minus alpha, so that's going to be 0.975. Same degrees of freedom, so that's where we got the 8.231. So we go back up here, and we see that chi-square of 0.975 was 8.231, and chi-square of 0.025 was 31.595. Okay, so why are we looking this up? Well, we're practicing because the formulas we're going to use require that we go look these up based on the percentage here that we are interested in and the implied alpha. Okay, so here's the direct calculation. Now notice that this is a confidence interval. This is a little bit interesting here. This is a confidence interval for the variance. Okay, so the variance is the standard deviation squared. So we have to take the square root. So if we want the interval or lower bound for okay, hopefully that makes perfect sense. If this is given us sigma squared and we want sigma, then I can take the square root of this. So let me bring you back to slide 11 because this is the concise version. So notice this says, give me the lower bound and upper bound for sigma itself. And notice this time we've got the square root of that very same formula. Here we're missing the square root and we're calling it variance. Okay, so let's say I want to find a 1 minus alpha times 100% confidence interval about sigma. Take the square root of the lower bound and the upper bound of okay, talked about that already. All right, so let's look at an application here. This has to do with stock trading, and one indicator of the risk of stock is the standard deviation rate of return. So if you've got this really high standard deviation, that's pretty unstable, right? So maybe you want to invest in stocks that at least, if you can't predict them, obviously, but if you know that it's historically stable, then generally the stock market climbs. Generally, I said. So the following data represents a weekly rate of return in percent for Microsoft. So 15 randomly selected weeks. So let's get N involved. N is 15. We want 90% confidence. Let's get alpha involved. With the 90% confidence, that's implying an alpha of 0.10. And for the risk of Microsoft stock. Well, we need, from our sample here, if you look at our formula, it needs S squared. So it needs the sample variance, which is just the square of the sample standard deviation. Okay, so they didn't give us the sample standard deviation. Instead, they gave us a bunch of data. So let's drop that data into a calculator list. Sometimes you need to do that if all they give you is the data. Sometimes they'll give you the part you need for your formula right off the bat. So we're going to go into stat edit. I'm going to put mine in list 2. Oops, that should say 5.34.15. 63. Negative 2.38. Okay, I'm trying to do this kind of fast, so let me know if you spot me goofing somewhere. Okay, so I think I've got all 15 of them in there accurately. Let's go get one of our stats. Remember, I used list 2, so I'm going to select L2. Okay, now I need to use S sub x because it's a sample, it's not the entire population. So we're going to use 4.697. All right. They went 1 decimal place further, and so let's oblige them. So we'll make it 4.6974. Okay. Now remember that for the calculation, this part here, this is our lower bound. Here's our n minus 1. Okay, and this here is going to be S squared. And then down here we have to go look up the chi-square. So chi-square of, for the lower bound, is the 1 minus alpha over 2. Now remember, alpha was 0.10, so this would be equal to chi-square of 1 minus 0.10 divided by 2 is 0.05. So we're interested in chi-square of 0.95 with 14 degrees of freedom, 15 minus 1. Okay, let's go look it up. They're showing us what it should be, but let's go look it up. .95, 14 degrees of freedom, 6.571. Okay, so that's where they got this. And then for the lower bound, we're going to use chi-square of 0.05 with 14 degrees of freedom. Here's 0.05 with 14, 23.685. Okay, so that goes into our lower bound calculation. So here was our n minus 1, our s squared, and then chi-square of 0.05. When I calculate that, I've got the lower bound. Now remember, we didn't take the square root, so this is for the variance so far. And then when we plug chi-square of 0.095 to get our upper bound, we get 47.01. So we're 90% confident that the population standard deviation, well, this is incorrect because they didn't take the square root. So let's change that to variance. And we'll calculate the standard deviation ourselves. So I need a square root of 13.04. Okay, so 3.611. And the square root of 47.01. .85. Okay, so we're 90% confident that population standard deviation, I'm abbreviating everything here. You see I have very little space. 90% confident the population standard deviation rate of return of Microsoft stock is between 3.611 and 6.85. Okay, so here's everything you need in the singular slide. So based on the question that you might be presented with, you just need to extrapolate your degrees of freedom, and based on the alpha that's understood, you figure out which chi-square you're after. So let's do this. All right, I'm going to hit your e-text here and go to page 454. Okay, and we're going to take a look at this pH of rain. Okay, so there's only 12 almost fits. Just move that over a little. All right, so there's only 12 pieces of data. So in order to do this, we need to know that it comes from an underlying normal population. And they've told us again that the data could come from a population normally distributed based on a normal probability plot, and that there are no outliers. So we can go ahead and use our formulas. Put this in L3. All right. All right, from list L3, we're going to grab our S sub x of 0.3218. I'm going to round it 4 places. Okay, guess what? The problem itself, so now you get to see it both ways. If they give it to you versus if you have to go calculate it on your own. I might have fat fingered one of these. This says S equals 0.319. And we're going to construct a 95% confidence interval. So alpha equals 0.05. So alpha over 2 equals 0.025. And we need chi-square of 1 minus alpha over 2. For our upper bound. And we're going to use 11 degrees of freedom. Okay, so we come over here, and for 0.975 and 11 degrees of freedom, it's 3.816. I need chi-square of alpha over 2, 0.025, also with 11 degrees of freedom. $21.92. Okay, so our confidence interval is going to be calculated by a square root of n minus 1, which is 11, times 0.319 squared divided by chi-square of alpha over 2, which is this one, 21.92. And then our upper bound is the square root of 11 times 0.319 squared divided by chi-square of 1 minus alpha over 2, which is this one, 3.816. Remember, the larger one has to be on the lower bound because it's in the denominator and it's going to divide this fewer times, making a smaller number. This will fit in there more times, making a larger number. Okay, so if we calculated those out, we should get the lower band of 0.226. And the upper band of 0.542. Okay, so this is just saying that we are 95% confident that the pH of rain in Tucker County, West Virginia, the standard deviation is between 0.226 and 0.542. Okay, so that's a summary there of confidence intervals for standard deviation. So we've estimated proportions, we've estimated means, and now we've estimated standard deviations. And yeah, I guess that's all I want to say about that. Okay, so I'll just put up an assignment for a little practice on this. Let me stop the video.